we discussed about the Reynolds transport theorem, and we developed how Reynolds transport theorem can be derived, and we developed a relationship between the system property and the control volume property. So on your screen, you can see the Reynolds transport theorem. That is, total derivative of the system property is equal to the partial derivative with respect to time of the control volume property plus the net change in the property that is flowing into the or flowing out of the control volume. If I expand these two terms, that is partial B by partial T, we know that B is basically mass time small b. Capital B is the extensive property and small b is the intensive property. And we know that mass is density into volume, so rho B dV, the volume part. And this integral is over the whole control volume. So we have done this replacement here. We have replaced it here. And we know that the total net flow, we discussed yesterday how it is written in this form. Okay. So if the flow is steady, or if there is no change with respect to time, the first term would be 0, right?
Yes.
So in most of the cases, when there is no inflow, when there is no change with respect to time in the control volume, then the first term will be called steady term, and it would be 0. Can you give me an example of any scenario in which the second term is 0? Any scenario you can think of that in which the second term is equal to 0?
Sir, जब perpendicular
डॉट प्रोडक्ट 0 हो जाए.
And that would be physically, उसका क्या मतलब होगा? What would be the physical meaning of that?
सर के सरफेस से के पैरेलल वो फ्लूइड फ्लो कर रहा है.
Flow is not into the control volume, right? There is no inflow or outflow from the control volume, right? This can be one scenario when there is no inflow and there is no outflow. What can be another situation? Can there be another situation when this term is 0? Is there any other situation in which this we can use this?
Velocity is 0.
Again, that would be the same when there is no inflow or outflow. That can be that velocity is 0, the flow is parallel to the control surface. The second situation is when the mass coming into the system is equivalent to the mass going out of the system. That is, the inflow is equal to the outflow. The net flow would be 0. So this term would be 0 in that case, right?
Yes, sir.
Clear? So here is a situation when we see this situation and we analyze it with respect to the Reynolds transport theorem. So this is the situation, and I ask you to apply it on the Reynolds transport theorem, apply Reynolds transport theorem on it. So what will happen here? This is your control volume. This imaginary line or this dotted line is representing your control volume. And these are your control surfaces. These red lines, like I'm drawing, these are your control surfaces. The velocity at the inlet and the outlet is same. So if I talk about this term, for the first part, integral control surface rho b. What is v dot n here for the first part? For the control surface 1, if I call it control surface 1.
Sir, -1.
It is v dot n is?
Sir, minus
less than
minus v naught, right?
Yes, sir.
Into dA. And if I write about the second term at the control surface 2, we'll be writing control surface 2 Here, this is the control surface 2. What is happening here? Here, V is in the I direction, right? And the area vector and the I are parallel. So V dot N is positive, right? So it is outflow. So the second term is rho B, V naught, B A. So what will happen? These two terms will cancel out, right? Is it clear?
Yes.
So the only term that would be governing the control volume change would be the first term, this unsteady term, the local term, right?
Yes, sir.
We see another example to further clarify our concept of the how that will be applying to the control surface, how this concept will help us. So this is a problem here, and this is its pictorial description. So wind is flowing across a steady state field with an approximate velocity profile as shown in figure. Wind is flowing in this profile. That from 0 to 10 feet it is changing, the velocity of the wind is increasing, and then from 10 to 20 feet it is constant at 15 feet per second. You are required to calculate the momentum flow rate across the vertical surface with the parameter b, that is the small b, equal to the velocity. We already discussed that if we replace b by velocity, that equation would be giving us the change in momentum, right? Because capital B is m times small b, and if small b is velocity, then capital B is
Momentum.
momentum. So the question is asking you to calculate the momentum flow rate, that is rate of momentum with respect to time, dp by dt, right? So we are required to calculate this. We use the Reynolds transport theorem. We read the statement again, and if we read the statement, the wind having density this blows across a steady field, which means that the first term in the Reynolds transport theorem would be 0, that is partial by partial t triple integral, or I will write a single integral over the control volume rho b dv. First term ऐसी थी जी, was it like that? Which is miss तो नहीं कर रहा? There is a velocity term here, rho b. No, it's like this. Okay. So v is velocity, so I will write rho v here. Okay. Rho v, the velocity v. This term would be 0, right? Then we have the second term, that is integral control surface rho b v dot n dA, right? Here in this case, b is again, this b is will be replaced by the velocity. So I'm writing that velocity in red. V dot n would be, if the flow is in this direction, V dot n would be, this is the velocity vector, and this is the area norm.
-1.
Negative ऐसे
That
ही.
is I. Negative I, so it would be negative. So we'll write dp by dt equal to minus integral control surface rho v, that is a replacement of the b, into v dA. So the integral would be equivalent to rho v square, integral over the control surface rho v square dA with a negative sign. Clear? Is it clear?
Yes, sir. Clear.
Now how to solve this integral? We know that velocity has two parts, from 0 to 10 feet. So we need to know the velocity function from 0 to 10 feet and then 10 to 20 feet, right? So we know that from 0 to 10 to 20 velocity is fixed. That is, we will break this integral into two parts. That is equal to minus. First part will be from 0 to 10. Density is constant, so I'm also taking it outside the integral here. The rho 0 to 10 v square dA plus 10 to 20 v square dA, right?
Yes, sir.
From 10 to 20 feet, we know that velocity is fixed at a rate of 15 feet per second, right? So I will just replace this velocity square with 15 square, right? उसमें तो कोई इशू नहीं होगा हमें, right? 15 square here. What about from 0 to 10 feet? It's a linear increase, right? From 0 to 15 feet. So we need to know this function. कैसे निकालेंगे ये function जी?
Slope
Equation of line.
We know that simply if I take this area y equals to mx plus c, this equation, right? If I define this as the y coordinate and if I define this as the velocity coordinate, so this would be m v plus c, right? ऐसे ही होगा जी.
Yes, sir.
So first we need to know this slope m. Can we calculate this m? Anyone?
Yes, sir. 10 minus 0
At
4 divided by 15 minus 0.
I'm writing the coordinates v comma y, okay? Because v is the horizontal axis and y is the vertical axis. First coordinate is they are 0 0 at y0, v is 0, and the second point is at
15, 10.
v is 15, y is 10. So what is the slope? 10 minus
10
0
minus
divided
0.
by 15 minus 0. So
2
10
by
by
3.
15 or 2 by 3. This is the slope. What is c?
10, sir.
0, 0. 0.
So it is 0. c is 0. So the equation of velocity would be v would be 3 by 2 times of y, right? Clear?
Yes, sir.
So we'll replace this v square by 3 by 2, which would be 9 by 4, right? 9 by 4 y square. Clear?
सर एक
Yes, sir.
सेकंड स्क्रॉल अप कर सकते हैं.
Yes, please. Here.
ठीक है सर, सही हो गया.
Now the next question. What is how to solve this dA? Because we consider this dA, this would be a double integral, right? This should be dx into dy, right? And this should also be dx into dy. So how to solve this integral?
सर ये y square dA वाला जो हमने इंटीग्रल पहले सॉल्व किया था वही बन जाएगा.
So if we see the problem statement, we can see that assume the width into the paper is equal to unity, right? So dA would be equal to dx into dy, and if dx is the coordinate into the paper, then it would be unity, and if it is unity, then it would be equivalent to dy only. Clear? So dA equals to dy. Is it clear?
Sir,
So
could you explain this?
Because it should be a double integral. No? dA should be a double integral. But the question has explained that the area is based on only one parameter, because the other parameter is equal to unity. Let me draw here. We know that area will be calculated based on the flow is across this cross-sectional area, right? This is your dA, and if this is dx, this base, and this is dy. So dA would be dx into dy, right?
yes, sir.
But the problem has told you that assume the width into the paper equal to unity, that is dx is 1, right? So this is equal to 1. So area will only vary when we can only vary the area with dy, right? So dA is only equal to dy, or we just multiply 1 by dy, it would be dy. Clear?
Yes, sir, clear.
So we'll replace this dA by here and by dy. So now can you solve this integral?
Yes, sir.
Density is given to you, limits of the integrals are defined, you just need to integrate. This would be y cubed by 3, and then you will apply the limits from 0 to 10, and this would be 225 into y, applying limit from 10 to 20. So you just solve these integral and you will get the answer. You need to keep one thing in mind, that the result of momentum is a vector quantity, right? Momentum is a vector quantity. Is it clear?
Yes.
So this result should also be a vector. So in which direction would momentum be changing?
Why?
If this is the conventional ijk direction, v dot n should be equivalent to
So negative or
it should
minus?
be I, right? Minus we have already included in the question here. So we'll be writing an I here, right? So this will be with an I. Clear?
Yes, sir.
And what would be the unit of this? Unit of the result?
kg meter per second.
Momentum is mass time velocity, right? So in maths, the units of the problem are in English system, so you need to answer in English system. Mass is
feet per second.
slug and velocity is
second.
feet per second. So this is momentum. So rate of momentum would be slug feet per second.
Per second हो जाएगा ना?
Per second square.
Per second square हो जाएगा.
Slug feet per second square. Is it clear? So is the problem statement clear now? Any question in this problem?
सर ये इसकी डायरेक्शन जरा वो कर दें, इससे इंटीग्रल का आंसर जो है वो ओवरऑल पॉजिटिव में आया और बाहर जो नेगेटिव लगा तो उससे नेगेटिव हो जाता है ओवरऑल आंसर ना, तो इसकी डायरेक्शन फिर किस तरह होगी?
ओवरऑल आंसर जो पॉजिटिव आएगा आपके पास, आप सॉल्व करें एक बार जरा इसको।
सर इंटीग्रल का आंसर जो है वो पॉजिटिव है।
तो बाहर जो
Negative
नेगेटिव है वो, जो बाहर नेगेटिव वो क्या बता रहा है? दैट मोमेंटम इज
सर वो नेगेटिव डायरेक्शन है।
स्लोइंग
How
डाउन,
that?
ठीक है,
ओके
ठीक है, द रेट ऑफ मोमेंटम इज डिक्रीजिंग विद टाइम,
यस सर
इट इज अगेंस्ट द फ्लो, क्लियर?
ओके जी।
एनी क्वेश्चन एल्स? कोई और कोई कंफ्यूजन तो नहीं है इसमें? ये तो आगे बढ़ते हैं, विल मूव फॉरवर्ड।
सर एक क्वेश्चन था जो पिछली हमने इक्वेशन पढ़ी थी, उसमें ट्रिपल इंटीग्रल्स थे, वो 3 इंटीग्रल्स क्या बता
तो
रहे
इसमें
थे?
सर ये नेगेटिव एक्स एक्सिस ही है।
You are not still clear about the direction? Let me redraw it here. This is your a control surface, right? And this is your velocity direction, v. Clear? The area normal of this control surface would be in this direction. This is the normal vector. And if we take this as the x direction, this would be I with a negative sign, right? So we have rho v, which is replacement of v, into v dot n, right? So this v is in the I direction. So if I write the scalar form of it, that would be v magnitude into I. Clear? And if I write the scalar form of the second v, that would be v into I, because it is the same v. And finally, I take the dot product with n, that is negative I, right? ये clear है जी चीज? Is it clear?
Yes, sir.
So I dot I would be 1, but there will be a negative outside, right? Minus v square into I. The result of this equation would be like this, right? Minus rho v square into I. So is that clear?
Yes, sir.
जिन दोस्त का सवाल तुमको क्लियर हो गया?
सर मेरा सवाल था, जो 3 इंटीग्रल्स बने हुए थे जो स्टडी फ्लो के, वो 3 इंटीग्रल्स क्या बताते हैं? ट्रिपल जो बने हुए थे साइन,
आप
वो क्यों बने?
haven't you studied the volume integrals and the area integrals in calculus or analytical geometry?
जी जी सर,
पढ़े हैं?
तो नहीं,
No.
इस तरह क्लियर किया आपने।
If I write this as rho dv, just to explain you, not it's a concrete, not a concrete thing. What does this dv mean? The integral over the volume, and volume is basically combination of 3 dimensions, right? dx, dy, and dz. ऐसे ही है? So it means I
जी
have
सर।
to integrate this single integral 3 times, one with respect to x, one with respect to y, and one with respect to z. Clear?
यस सर।
So if I say dx is constant, it means there will be one integral will be eliminated, the internal one. If I say dy is constant, the second one will be eliminated. The volume only changes with change in z. Let's say I have a surface like this. Let's say I have a rectangle. I have a cube like this. Its volume would be equal to, this is the dz direction, this is the dx direction, and the one into the page is this one, like say, not here, I can say this dy. I say dy is fixed value of, let's say, 1, dx is fixed value of 1, but dz is a variable. I can increase its height like this from in different forms. So the volume will change with change in dz.
dz.
So I will only integrate with respect to z. I will keep these two constant. Clear?
Yes, sir. Clear.
If all of these three are variables, I can change dx, dy, then I will have to integrate this term 3 times. One with respect to dx, the variation with respect to dx, the variation with respect to dy, and the variation with respect to z coordinate. Clear? So these are some of your homework problems from this chapter. These are quite easy problems, and like the problems we have already solved, you just need to go through them and solve them. And if you have any confusion in these problems, then we can discuss them in the next class. Moving on, we'll be starting with chapter number 5, the finite control volume analysis. This chapter is based on the Reynolds transport theorem. Now we are very much familiar with the Reynolds transport theorem. We know how we derived it. We know the meaning of the terms in the Reynolds transport theorem. Now we will be replacing property B with different variables, different properties. Let's say we will be replacing small b with unity. Then we will have capital B as mass, right? So we'll get the continuity equation. So this will give us continuity equation. When we replace small b with velocity, we will get the linear momentum equation. And when we'll replace small b with v square by 2, we'll get the energy equation. So in the next chapter, we'll be replacing these quantities and we'll getting the continuity equation, linear momentum equation, and the energy equation. And then one by one, we'll be discussing these equations in details. So in the next class, we'll start with the continuity equation, then we'll discuss the momentum equation and then the energy equation. So any question from today's lecture?
एक्सक्यूज मी सर, एक सवाल था सर कि ये मोमेंटम की यूनिट इन इंपीरियल सिस्टम सर ये क्या बनेगी सर? मेरे पास जो आंसर है उसके हिसाब से मेरी इक्विवेलेंट यूनिट स्लग पर फीट आ रही है सर ये सही है?
Whenever you're confused with units, just stick with the basic. Momentum is P. Formula तो change नहीं होता ना, P, and it is equivalent to mass into velocity, right?
Yes, sir.
Mass is slugs in imperial system, right?
Yes, sir.
And velocity is feet per second. Now the Reynolds transport theorem is calculating rate of change of momentum, that is dP by dt, that is change of momentum per unit time. So this will give us, you will divide the unit of momentum with time, slug feet per second divided by second. So it would be slug feet per second square. These are the units you should get. Clear?
Yes, sir.